So, the background for this study case is bridges are critical infrastructure components that are require constant monitoring to ensure safety and longevity. Over time, factors like heavy traffic, weather conditions, and material degradation can compromise their structural integrity. Traditional inspection methods are time consuming, costly, and often reactive rather than proactive. So, for the problem statement on this study case is design a computational solution to monitor and optimize the structural health of a bridge. The solution should consider 1. Real-time sensor data, 2. Early detection of potential structural issues, 3. Prioritization of maintenance tasks based on severity, and 4. Cost effectiveness and scalability for large-scale deployment. So for the key variable is 1. Real-time sensor data, data from sensors like strain gauges, vibration sensors, temperature sensors, and so on. The second one is bridges structural health, indicators like strain, vibrations, and cracks. The next one is environmental factors, weather, traffic, and other external factors affecting structural integrity. And the last one is cost, cost associated with sensor installation, maintenance, and repairs. So the challenge that may happen in this case study is 1. Communication delay. Latency in data transmissions affects real-time monitoring and can delay the detection of structural issues. The second one is network scalability, managing large-scale deployments without overwhelming the network, ensuring interoperability among different sensors with varying protocols and requirements. The last one is environmental factors. Sensor sensitivity to environmental conditions such as extreme temperature, humidity, or electromagnetic interference can affect the accuracy of the collected data. So the pattern recognition for this study is 1. Regular data collection. Sensor data is continuously monitored at regular intervals. This pattern of regular updates is crucial for detecting any gradual or sudden changes in the structural health of the bridge. The second one is repeated analysis of data. After each new sensor reading is collected, the system checks it against predefined thresholds or compares it with historical data to identify anomalies. This process is repeated as new data is generated. The third one is routine maintenance checks. Maintenance tasks are carried out repeatedly based on sensor data findings. For instance, if a sensor detects an anomaly, the same steps may be followed repeatedly to assess the severity of the issues and determine the need for maintenance. The last one is trend monitoring. Data trends such as increasing strain or vibration levels over time will repeat across different parts of the bridge or over time. Identifying these trends helps predict potential failure points before they become critical. So for the decomposition, the first one, sensor capabilities. Vibration, strain, and temperature sensors are installed to monitor the bridge structural health in real time. The second one is condition monitoring. Data is collected continuously under varying weather conditions and traffic loads to assess the bridge current state. The next one is issue detection. The system identifies early signs of stress or strains anomalies, helping detect potential structural failures. The last one is maintenance optimization. Maintenance tasks are prioritized based on the severity of the detected issues to ensure cost-effective repairs.
Data representation. To achieve the vibration, use meter, an IoT device, to measure vibration in real time. To achieve the strain, use strain gauge to measure strain surface. To achieve the temperature, use an IoT device called DHT2222 to monitoring the temperature sensors in real time. To achieve the wind speed, use anemometer to measure the wind speed. To achieve the wind direction, use wind vane to measure wind direction. This is the form of its computational data. Vibration float, strain integer, wind speed float, wind direction integer, temperature float. Integer, a number with no decimal or fractional part, and it includes negative and positive numbers, including zero. Float, a data type used to represent numbers with decimal point.
The next thing is the most suitable algorithm for this case. For detecting structural issues quickly, we use linear search. Since sensor data is constantly changing and needs real time monitoring, a linear search efficiently checks all sensor values against the threshold. And the next thing is for identifying the most critical issue, which is finding extreme values, min and max. If we need to find the sensor with the highest recorded vibration, finding the maximum value is ideal. And the next thing is the for efficient and maintenance scheduling, greedy algorithm. If maintenance tasks must be prioritized based on severity, a greedy approach can sort issues and handle the worst one first. Example, sort issues by severity and fix the most critical ones first. And the last but not least is for brute force analysis worst case scenario, brute force search. If we want to analyze all sensor data combinations by identifying failure patterns over time, a brute force approach could be used.
So here are the flow chart. We begin with the start, then we collect the data such as vehicle load, ambient temperature, then the data is collected and processed. Then we analyze the data for anomalies. If it's normal, then we can go back to the collection of data. If it's abnormal, then we can process by security early warning. Then determine if it's safe or unsafe. If it's unsafe, then print repair, then end. But if it's safe, then we can print maintain and back to the first step, which collect the data. So here are the pseudocode for the flowchart. So we begin with the start, then collect the sensor's data, process the collected data, and then analyze the processed data for anomalies, check if the data is normal or abnormal, and if the analysis result is normal, then we can continue with regular monitoring. Else, if analysis result abnormal, then proceed to security, early warning, and damage assessment. Then trigger security early warning, assess damage, check if the structure is safe or unsafe. If safe, maintain the structure. Else, if damage status is unsafe, then initiate repairs and print structure is unsafe, proceed with repair, and then end the process.
Okay, so the next step is the big O calculation where we are going to calculate the worst case or the big O. So in order to do that, you need to follow these steps. So the first step is for the collect sensor data. The worst case, all sensors are active and data collection takes linear time. And the complexity is ON. Then for the second step is the process and analyze data. The worst case is every data point has to be reviewed for any irregularities, where the complexity is ON. And the next one is check if data is normal or abnormal. So the worst case is every data point must be analyzed individually, and the complexity is ON. Then for the next step, um, for the security, early warning, and damage assessment, the worst case or big O is all detected issues require assessment, and the complexity is ON. The next one is sorting issues by severity, sorting is news. The worst case is sorting all detected issues before action, and the complexity is O n log n. And for the last step is the repair decision process, where the worst case is every structure needs maintenance or repair, and the complexity of it is ON. And the final worst case complexity is we need to add all these up. So T worst equals to ON plus ON plus ON plus ON plus ON log N plus ON. And the answer is ON log. So I think that's all.
In the test algorithm, the first thing we have to do is explain what is in the test case. So there is three things in the test case. First one is sensor data, which the system have to collect vibration, strain, and temperature data. And then next is expected behavior. The system detect extreme values indicating potential structural issues. And last one is the result, which the system have to correctly detect extreme sensor values and generate alerts. So in the algorithm test steps, the first step is simulate normal condition. The system have to feed normal sensor reading into the system. For example, the sensor reads vibrations on 0.5 and the temperatures on 25 Celsius. Second step is introduce anomalous readings. It injects abnormal values in the system, and the algorithm should indicate these anomalies. In the third steps, the monitor system response. The system have to check the system triggers alerts when anomalies exceed the safety threshold and validate whether alerts are ranked based on severity. And the last step is evaluate maintenance recommendation, which the system have to verify suggest appropriate actions such as immediate inspection, minor repair, or emergency shutdown. So the improvement of this algorithm is implement AI-driven predictive modeling to anticipate structural failures.